Today we'd like to explore the idea of the center of mass or the center of gravity of a rigid object. For instance, take this rod, and if I try to balance it on my finger at a certain point in that rod, I'm balancing it via the gravitational force, and this point is often referred to as the center of gravity of the rod. Now, if we were in empty space with no gravitational field, then center of gravity doesn't make any sense, but this point still coincides with what we call the center of mass of the object. And now I'd like to define center of mass. So let's consider our rigid body, and we'll just describe it as some object. We'll make it idealized. And that there's going to be trying to find some point in this object, and we'll identify that point as the center of mass. Now, let's imagine that this rigid body is made up of a bunch of little pieces. So we have mj, and this jth piece is located from the center of mass, a vector rcm. Now, how we want to define this particular point is that when we make the sum from j equals 1 to n over every single point in this body, then that will be 0, and this will be the definition of the center of mass. That when you add up the position vector with respect to this point, weighted by the mass, and you add up all of those vectors, you'll get 0. Now, if you don't know where the center of mass is, then this is difficult to calculate. So let's find a way where you choose an arbitrary point, and let's write that arbitrary point, say, over here. We'll write it like this, S, and we'll treat that as our origin. And I'll draw a vector rsj, and here I'll draw the vector rcm. And now what we have from our vector relationship is that the vector rsj equals the vector rcm, and that's what I want to find, plus the vector rcmj. And now let's add up, multiply each of these by the mass, and make a sum. So we have mj rsj equals the sum of mj. Now, the vector rcm, this vector, no matter where we picked a point in this object, this vector is always the same. And that's why I pull it out of the sum. And over here, I have the sum from j goes from 1 to n, it's j 1 to n, of mj rcmj. Now recall, this is precisely how we define the center of mass point, that this is 0. And so we can now conclude that the center of mass, so you pick an arbitrary point, and if you want to find that vector to the center of mass, what you do is you make the sum from j goes from 1 to n of mj rsj, and you divide that by j goes from 1 to n mj. And this is what we call the center of mass. So conceptually, the center of mass is the point in the object where if you take a vector to any of the little mass elements and you weight it by the mass element and you add them up, you get 0. If you wanted to calculate the center of mass about any point, you choose a point S, you draw the vector from S to the object, you sum up those vectors. We see by our vector triangle rule that we can now calculate that center of mass vector by this equation. And now, let's just rewrite this, because this is the total mass. And what we see is that rcm equals j goes from 1 to n mj rsj divided by the total mass. Let's try to find the center of mass of a uniform object like a uniform rod. And let's assume this rod is length L, and we want to find the center of mass. Now, before I begin this calculation, you can probably already guess that it's going to be exactly in the middle, and we'll verify that. But let's first define what we mean by our center of mass for discrete particles. Recall that this was a sum over all the particles in the system. So we'll take a label j goes from 1 to n. And it was the mass of that jth particle times the position vector of that jth particle with respect to some origin. And we're dividing that by j goes from 1 to n of the total mass in the system. Now, how do we translate this equation for a continuous system? And let me just again show that we had chosen an origin. Here was our jth particle of mass mj and rj. So what we want to do is draw the analogy, and here's how it works. That for each discrete particle, we're going to look at that as some mass element, delta mj. Our vector rj will go to a vector for this mass element. I'll just write it delta m. And our sum from j goes from 1 to n is actually going to go to an integral over the body. So let's see how that looks. So first we'll do it with the total mass. M, here we're summing over j from 1 to n of mj. That goes to the integral over the body. Now, the delta m, when we take limits, because that's what an integral goes, we'll write that as dm. So that becomes a limit over the body. And likewise, our sum, j goes from 1 to n, of mj rj, goes to an integral over the body of dm vector r going to that element. So we can say in the limit that this becomes r going to that element. Now, that means that our continuous expression for the continuous object is an integral over the body of dm r to that element dm divided by an integral over the body of dm. I'd now like to talk about the velocity of the center of mass for a system of particles. So let's take a system, which I'll just outline by this. And in that system, we have a bunch of particles. Particle 1, particle 2. Let's refer to this as the jth particle. And some point xcm. And if I want to talk about the position of the center of mass, I can choose a point S. And if I want to define that vector rcm, then what I have to do is draw a vector to each object, rsj. And we saw that this velocity, the position of the center of mass, with respect to this origin S, is the sum mj rsj. And that's divided by the total mass m total. And j goes from 1 to n, where n is the number of particles in the system. Now, if I want to find the velocity of the center of mass, then I can just differentiate this. And I'm dropping the point S for the moment, but let's just differentiate 1 to n, and you'll see why. And when I differentiate the position vector of the object, that's the velocity of the object, divided by j goes from 1 to n, the total mass. Now, why did I drop the position? Because if you have any two fixed points, so if I chose another fixed point, say over here, p, then this distance, r, we'll call a vector from s to p, rsp, this is a constant. And if I draw the position vector with respect to p, now the point here is that this is constant distance because this is a fixed, these are fixed points. Then if you were to draw your vector triangle, which is the position of the object with respect to s, that's this vector, is equal to that fixed position vector from s to p, plus the vector from p to j. And I differentiate this, drs j dt. Well, this derivative of a constant vector, this is 0, plus drp j dt. And so we see that the velocity j is independent of the choice of point S. You choose any other fixed point, and you get that these velocities, drs j dt equals dr p j dt for all fixed points p. And that's why in this expression, when we differentiate the velocity, even though we had an index s, we drop that. And so our conclusion is that we can treat that we have the velocity of the center of mass of this system is equal to the sum mj vj, j goes from 1 to n, divided by the total mass. Now, what's interesting here is why is this an important quantity? Let's just add that if we want to talk about the acceleration of the center of mass, I do exactly the same type of calculation. I just differentiate, and I get the mass of the jth particle times the acceleration of the jth particle divided by the total mass. And our next step is to understand why this is an important quantity for a system of particles. We'd like to consider a system of particles. Say we have object 1, we'll call this the jth object, object n, and somewhere in the system of particles is a center of mass. Now we know that the external force is causing the momentum of the system to change. And what we'd now like to show is that we can reduce this system to an effective single particle. The way we'll do that is recall that the momentum of the system is given by the sum of the individual momentums. We'll call that the jth particle, where we're summing j from 1 to n, and that's the sum of the momentums of the various particles. Now, when you differentiate the momentum of the system with respect to time, we're just differentiating the velocity, and so that becomes the acceleration of the jth particle. Now, we saw when we defined the center of mass that the acceleration of the center of mass times the total mass of the system was equal to this sum of mj aj. J goes from 1 to n. So we see that another way to think about how the momentum of the system of particles is changing is simply the total mass times the acceleration of the center of mass. And our combination of Newton's second and third law now becomes that only the external forces cause the momentum of the system to change, so that's equal to the total mass times the acceleration of the center of mass. Now, what does this equation really mean? So let's draw our pictures again. Here's our system. We have particles 1, etc. That's the jth particle, n particles, and in here is the center of mass. Now, I'm going to outline my system like this, and what this equation is telling us is that we can just focus by putting all of the mass, m total, at the center of mass, and that center of mass is going to move according to some trajectory, and all we have to think about is this is now a simple, this is a point particle of total mass m. M total. So what we've done is we've done a very important reduction. We've taken a complicated system of particles and reduced it to a single point particle of total mass m located at Cm. And the dynamics of that total particle is if there is an external force acting on this system, we place this external force at the center of mass, and now we can calculate the acceleration of the center of mass is just that external force divided by the total mass. And that's how we can reduce this complicated system of particles to a translational motion of the center of mass. Now, we still cannot describe the individual interactions in the system, but we're not trying to do that anymore. We're not trying to trace how each particle moves. We're just looking at our system as a point particle and talking about how that point-like object is translating in space. And this is a powerful tool that we'll use again and again and again.